Welcome to today's lecture on types of electric drives and their functions. Myself, Dr. Shimpir Alhan, Professor, Sri Shankaracharya Technical Campus, Bhilai. In the previous lecture, we have already discussed the fundamentals of drives. Today, we will explore the types and functions of drives, covering the classification and the functions they perform, such as speed control, torque control, position control and efficiency enhancement. Electric drives can be classified based on various factors such as type of power sources they use, that is AC or DC, the method of control, open loop or closed loop, and the application they are designed for, including industrial, domestic and automotive sectors. Now, let us have a look on classification of electric drives. Based on power source, we have AC drives and DC drives. AC drives are powered by alternating current and are commonly used for controlling the speed of AC motors. AC drives include variable frequency drives, also known as VFDs, which are used to control the speed and torque of AC motors by varying the frequency of the supply voltage. They find wide application in industry such as conveyor systems, pumps and fans. AC drives are generally, if we see, they are more efficient, have a longer lifespan and are suitable for applications where speed control is required over a wide range. But they can be more complex and expensive to implement if we compare them to DC drives. Now, coming to DC drives, they are the systems that control the speed, torque and direction of DC motors using direct current. They are typically used in applications which require high starting torque and smooth speed control, such as in elevators, cranes and electric vehicles. If we look at the advantages, DC drives offer precise speed control and high starting torque, making them ideal for specific industrial and transportation applications. And talking of disadvantages, they require more maintenance due to presence of brushes and commutators and are generally less efficient than AC drives. Drives are also classified as open loop and closed loop based on the control method. In an open loop system, the drive controls the motor without feedback from the output. The system sends a control signal to the motor and assumes that the motor performs as expected without checking the actual output. Open loop systems, if we say, they are simpler, cheaper to implement, and their use in applications where precise control is not critical, such as in basic fans or simple conveyor belts. Now, if we say the disadvantages of the open loop control system, they lack the feedback mechanism, which means that these systems are less accurate and can suffer from errors due to load changes or other external factors. In a closed loop system, feedback from the output is used to adjust the control signal to the motor. Sensors measure the actual performance. For example, it can be speed, it can be position, and the system adjusts the input to maintain the desired output. The closed loop systems provide precise control, making them suitable for applications where accuracy is critical, such as in robotics, CNC machines and elevators. They are more complex and expensive to implement, but the benefits of accuracy and reliability often outweigh these drawbacks. Now, based on the applications, we have industrial, domestic and automotive drives. Industrial drives are used in manufacturing and processing plants to control machinery and processes. They are crucial in controlling motors which are used in conveyors, pumps, fans, mixers and other industrial equipments, such as AC drives in conveyor belts and DC drives in rolling mills. The domestic drives, if we see, they are used in household appliances and consumer electronics. They control small motors found in everyday devices like washing machines, refrigerators, air conditioners and fans, such as variable speed drives are used in washing machines and motor drives in HVAC systems. Next, coming to the automotive drives, they are used in vehicles to control various motor functions, including those in electric vehicles EVs and hybrid electric vehicles HEVs. These drives manage motor operations such as propulsion, steering and braking. The examples are DC drives in electric vehicles and AC drives in hybrid vehicles. After looking into the classification, let us delve into the 4 fundamental types of drives, each catering to specific requirements and applications. Let us start with the DC drives. They are among the oldest type of electric drives traditionally used in applications where the speed control has to be precise, such as cranes, hoists and elevators. They regulate the voltage across a DC motor to control its speed. We have already seen this when we have covered the DC machines in the previous lectures. These are known for their excellent torque handling capacity. DC drives are particularly valuable in applications where we need robust control from the start, such as in lifting heavy loads with a crane where starting torque and smooth acceleration are critical. They consist of a DC motor, a controller that regulates the motor speed and torque and a power supply. Whenever there is a demand for a wide range of speed control in either direction, as in reversible drives with better regulation and simplified mode of control, the best choice falls on DC drives. For example, rolling mill drives, paper mill drives, etc. Now, DC motors have the advantage of ease of operation at different speeds. The operating characteristics can be easily varied, but DC motors are most expensive of all. The DC shunt motors, if we see, they are constant speed characteristic motors and are used in rolling mills, paper mills where speed control has to be precise and it is very necessary. The Ward-Leonard method of speed control incorporating continuous feedback permits smoother operation and greater accuracy here. The various type of DC motor drives are thyristor fed drives, chopper fed drives which are mainly used in medium or small sizes, and small servo type of drives. Let us have a look on them. A separate thyristor or diode rectifier is used to supply the field of the motor. The power is much less than the armature power, so the supply is often single phase. If we talk of motors up to few kilowatts, the armature converter can be supplied from either single phase or 3-phase mains, but for larger motors 3 phases always used. The arrangement shown in the figure is typical of the majority of DC drives and provides for closed loop speed control. We will discuss the function of 2 control loops in the coming slides. Here a low power control circuit is shown, and these circuits are used to monitor the variables of interest which are usually motor current and speed, and to generate appropriate firing pulses so that the motor maintains constant speed despite the variations in the load. The speed reference is typically an analog voltage varying from 0 to 10 volt and obtained from a manual speed setting potentiometer or from elsewhere in the plant where they are used. Next is our chopper fed DC motor drives, and these are mainly used in medium and small sizes. If the source of supply is DC, for example in a battery vehicle or a rapid transit system, a chopper type converter is usually employed. The principal difference between the thyristor control rectifier and the chopper is that in the former the motor current always flows through the supply, whereas in the latter the motor current only flows from the supply terminals for part of each cycle. This is important to note. The principal difference between the operation of two. Next is our small servo type drives. In the context of motors and drives, the term servo generally refers to systems designed for closed loop or feedback control, typically managing shaft torque, speed or position. Although we can say that there is no sharp dividing line between servo motors and ordinary motors, the servo type will be intended for use in applications which require rapid acceleration and deceleration. Now moving on to AC drives. These drives are integral in industries where motor speed needs to be varied. AC drives are more commonly used in modern applications due to their efficiency and versatility. The most common types are variable frequency drives, VFDs and servo drives. They are widely used in HVAC systems, conveyor belts, pumps, offering precise control over motor speed and torque both. By adjusting the frequency and voltage supplied to an AC motor, these drives can efficiently manage the motor's speed and torque, leading to significant savings in the energy, and also the operational efficiencies enhanced manifold times. If we see here, for AC drives, the cost is lower and the maximum torque varies directly instead of square of voltage. The various types of AC drives are synchronous motor drives and induction motor drives. Synchronous motors operate at a constant speed, synchronized with the frequency of the AC power supply. Unlike induction motors, there is no slip between the stator field and the rotor. Whereas if we see here, the synchronous motor drives, they have the ability to work as synchronous condenser for power factor improvement with better power factor at low speeds. The efficiency is higher than that of induction motor of comparable size. Synchronous motors though have some disadvantages also. The starting problems are faced here. A damper winding is required. If high starting and high pull-in torque is required, a double cage damper winding is used. Normally, if we see a synchronous motor drive, it has to produce a starting torque of 150 to 200%, pull-in or synchronizing torque of 110% and pull-out torque of about 175 to 180%. Synchronous motors are normally constructed in very large sizes. Motor generator sets, air compressors, pumps and other constant speed equipments are examples of synchronous motor drives operating as synchronous condensers. Let us see now induction motor cage drives. A cage induction motor is very rugged and sturdy. It has a lowest initial cost per installation, but efficiency and power factor are poor as compared to synchronous induction motor. In industry, cage induction motors have maximum applications and are used wherever speed control is not required. They are constructed in various sizes ranging from small to very large. Therefore, they have a very wide range of applications in industry such as water pumps, compressor, fans and line shafts to name a few. Pole changing induction motors may be used wherever two-speed operation is required. However, they cost 30 to 40% more than standard cage induction motors. The development of the PWM inverters for the speed control of the induction motor operating at constant V/F ratio has definitely kindled hope for replacement of DC drives by AC drives in the near future. The disadvantage of this type lies in poor control at low speeds because of stator winding resistance dominating over leakage reactance. This we have already seen when we have discussed the AC machines. Next is the wound rotor induction motor drives. Various speed control methods are available for slip ring induction motors as discussed in the previous lecture. The efficiency and the power factor decrease with decrease of speed. The cost is also higher. However, the operation of the slip ring induction motor incorporating an automatic slip regulator and a flywheel for intermittent duty is so unique that it is worthwhile to use it. So, wound rotor induction motors are used for flywheel equipped motor generator sets working under shock loading conditions. These motors are used for mine winder drives. They are also used for line shafts, pumps, lifts, cranes, haulage, etc. They are used in paper making machines, textile mills, printing press and other industries. Also, if we talk of reciprocating pumps, crushers, shearer and lump breakers in coal mines and ball mills in cement factories which require high starting torque, which may be 2 to 3 times the full load torque due to high inertia and friction at standstill. There we use slip ring induction motors which give very satisfactory performance during their operation. Next we have servo drives. These are designed for highest degree of precision control. They consist of a servo motor, a feedback system and a controller. Servo drives control servo motors which are used when exact position is crucial. These drives are commonly found in applications requiring precise motion control such as robotic, CNC and automated production lines. In a manufacturing robot, servo drives help achieve precise movements essential for tasks like assembly or welding, ensuring each component is perfectly aligned and executed. Lastly, stepper drives control stepper motors which operate differently by moving in discrete steps. These features make them perfect for applications where we need precise control over position without feedback from the motor, that is open loop control, such as in 3D printer and small CNC machines where each movement must be precisely controlled to create detailed objects layer by layer as the load is relatively small. In summary, we can say the type of drive selected typically depends on the specific need of the application, where it is the need for speed, control, torque or precision. Let us now have a look on the functions of electric drives. They perform the function of speed control, torque control, position control and efficiency enhancement. First, let us discuss speed control. This function is not just about making a motor run faster or slower. It is about optimizing machine performance across a range of operations. For example, in conveyor systems, speed control is essential to match the flow of materials, or in fans and pumps to adjust the flow rate according to the demand. The most common arrangement, which is used with only minor variations from small drives of say 0.5 kilowatt up to largest industrial drives of several megawatts, is two loop control. This has an inner feedback loop to control the current and hence torque, and an outer loop to control speed. When position control is required, a further outer position loop is added. A two loop scheme for a thyristor DC drive is discussed first, but the essential features are same in a chopper fed drive also. Later, the simple arrangements used in low cost small drives are discussed. A standard DC drive with speed and current control is shown in the figure. The primary purpose of control system is to provide speed control. So, the input to the system is the speed reference signal on the left and the output is the speed of the motor as measured by the tacho generator on the right. As with any closed loop system, the overall performance is heavily dependent on the quality of the feedback signal. In this case, the feedback signal is the speed proportional voltage provided by the tacho generator. It is therefore very important to ensure that the tacho generator is of high quality so that its output voltage does not vary with ambient temperature and is ripple free. As a result, the cost of the tacho generator often represents a significant fraction of the total cost, because we cannot make a compromise here. To get an idea of operation of the system, we will consider what will happen if with the motor is running light at a set speed and the speed reference signal is suddenly increased. Because the set or reference speed is now greater than the actual speed, there will be a speed error signal represented by the output of the left hand summing junction, as you can see in the figure. A speed error indicates that acceleration is required, which in turn means extra torque, that is more current. The speed error is amplified by the speed controller, which is more accurately described as a speed error amplifier, and the output serves as a reference or input signal to the inner control system. The inner feedback loop is a current control loop. So, when the current reference increases, so does the motor armature current, which provides extra torque and initiate acceleration. As the speed rises, the speed error reduces and the current and torque therefore reduce to obtain a smooth approach to the target speed. We will now look in more detail at the inner, that is current control loop, as its correct operation is vital to ensure that the thyristors are protected against excessive overcurrents. Let us discuss the current control. The closed loop current controller or current loop is at the heart of the drive system and is indicated by the shaded region. The purpose of the current loop is to make the actual motor current follow the current reference signal. This is done by comparing a feedback signal of the actual motor current with the current reference signal. When the difference of the current error is amplified, and using this amplified current error signal, the firing angle is controlled. Hence, the output voltage of the converter is also controlled. The current feedback signal is obtained either from a DC current transformer, which gives an isolated analog voltage output, or from an AC current transformer or rectifiers in the main supply lines. The job of comparing the reference and the actual current signals and amplifying the error signal is carried out by the current error amplifier. By giving the current error amplifier a high gain, the actual motor current will always correspond closely to the current reference signal. That is, the current error will be small regardless of the motor speed. In other words, we can expect the actual motor current to follow the current reference signal at all times, the armature voltage being automatically adjusted by the controller, so that regardless of the speed of the motor, the current has the correct value. Of course, no control system can be perfect, but it is usual for the current error amplifier to be of proportional plus integral or PI type, in which case the actual and demanded currents will be exactly equal under steady state conditions. It is important to avoid having too much current in the converter, and we have already talked about this. The current control loop helps to prevent this from happening. As long as the current control loop functions properly, the motor current can never exceed the reference value. Hence, by limiting the magnitude of the current reference signal by means of, say, a clamping circuit, the motor current can never exceed the specified value which is shown. The characteristics of the speed controller are shown in the shaded panel, from which we can see that for small errors in the speed, the current reference increases in proportion to the speed, thereby ensuring linear system behavior with a smooth approach to the target speed. However, once the speed error exceeds the limit, the output of the speed error amplifier saturates and there is thus no further increase in the current reference. By arranging for this maximum current reference to correspond to full or rated current of the system, there is no possibility of current in the motor and converter exceeding its rated value, no matter how large the speed error becomes. This electronic current limiting is the most important protective device of any drive. It means that if, for example, the motor suddenly stalls because the load ceases, so that back EMF falls drastically, the armature voltage will automatically reduce to a very low value, thereby limiting the current to its maximum allowable level. The first thing we should aim at is, when we are setting up a drive, is good current loop. In this context, the word good means that the steady state motor current should correspond exactly with the current reference, and the transient response to step changes in the current reference should be fast and well damped. The first of these requirements is satisfied by the integral term in the current error amplifier, while the second is obtained by judicious choice of the amplifier, proportional gain and time constant. As far as the user is concerned, the current stability adjustment is provided to allow to optimize the transient response of the current loop. In simpler terms, the component typically known as current error amplifier is more commonly referred to as current controller or current amplifier. The term current controller is quite accurate and straightforward. However, calling it a current amplifier can be confusing because it implies that motor's current itself is being amplified, which is not the case. So, be careful. In current control mode, the current is maintained at a set value and the motor's steady speed depends on the load. For instance, if the torque reference is set at 50% and the motor is initially stationary, it will accelerate at a constant half rated current until the motor's torque matches the load torque. Without any load, the motor accelerates quickly with the voltage increasing to maintain the specified current. Eventually, the motor reaches a high speed slightly above its normal full speed, where converter's maximum output voltage limits further current increase, stabilizing the motor's speed. Moving on to torque management. The closed loop torque control is a critical method which is used predominantly in the areas of automotive applications, specifically in battery operated vehicles, rail cars and electric trains. This system allows for control of vehicle's torque output, enhancing both performance and energy efficiency. For applications where a specified torque is needed regardless of motor speed, such as in line tensioning, the outer loop can be bypassed, and this loop is a speed control loop. Instead, a current reference signal is sent directly to the current controller through the torque reference terminal on the control board. Since torque is directly proportional to current, the current controller effectively acts as a torque controller. Adjustments for accelerating torque might be needed through a transient inertia compensating signal, typically managed via potentiometer or a digital preset. The mechanism of the closed loop torque control involves a feedback system that continuously adjusts the motor's torque to match the desired set point, which is typically determined by driver's input through the accelerator pedal as shown. Let us discuss the process in detail. If we talk of the driver's input, the driver presses the accelerator which sets a torque reference, say T ref. This is initial command that dictates how much torque the motor should generate. The reference is set based on driver's assessment of required speed and the power for current driving conditions. The torque reference acts as an input to the vehicle's control system, initiating a process where actual motor torque needs to align with this reference. So, coming to the end of this lecture, let us review what we have discussed today. We have discussed the types of electric drives based on various factors such as AC or DC based on type of power source, open loop or closed loop based on the method of control, and industrial, domestic or automotive based on the application they are designed for. We have also examined how electric drives are used for speed control, torque control, position control and efficiency enhancement. I hope that this will enlighten you on the topic, and thank you very much. Thank you.